Good afternoon, everybody. So I'm going to present you a mission concept which seeks to put a SmallSat into a Mars stationary orbit, or aerostationary orbit as it is called, primarily to monitor the Martian weather. And this is a concept that we have developed with our industrial partner, ExoTerra, and thanks to funding from NASA PSDS-3 program. So let me start by illustrating what we refer to when we talk about the Martian weather. So if we look at this image of Mars, a particular image of Mars taken by the Mars Orbiter camera on board the Mars Global Surveyor, you can distinguish different atmospheric phenomena. If we look into the southern hemisphere, we have a reddish, patchy area, and that corresponds to dust storms. If we look at the equator, in the equatorial region, we see these white patches. They correspond to water ice clouds, and we can spot the northern polar ice cap. The polar ice cap is formed by CO2 gas condensing on the ground, and possibly when CO2 snows down to the ground. And all these phenomena, these atmospheric phenomena, are connected, and they are connected through what we call the atmospheric circulation. So for Martian weather, we consider all these atmospheric phenomena at a short time scales. Okay, so this is what we focus on. And in particular, if we look at the dust aerosols, so we consider phenomena related to dust aerosols, we can distinguish four types of phenomena depending on the spatial scale. Dust dales are obviously the smallest of these atmospheric phenomena. They are like convective vortices. They are able to pick up dust and lift it higher up, a few hundred meters, but they are small. They have small diameters. Now, if we go further in the scale, on the left-hand side, we see an image from, again, Mars Orbiter camera. These correspond to smaller local storms, local dust storms, and they have fronts more or less a few hundred kilometers. On the right-hand side, conversely, we have the regional scale storms, and they are larger. They have larger fronts, even a few thousand meters. Up to the global scale, several regional scales can merge together and spread dust overall on the planet. This is, for example, a global scale dust event, we call it, that occurred in 2001, observed by Mars Global Surveyor. So we have different scales. What we focus on in this particular concept are the regional dust storms possibly leading to global scale events and the water ice clouds. So why do we need such a mission? Well, first of all, the dust and the water ice are both active, relatively active, so they absorb radiation, they heat the atmosphere and change the state of the atmosphere. So they affect the weather and the climate, obviously, the climate being just the long-term evolution of the weather. There is a serious need for continuous and simultaneous study and monitoring of these aerosols, because we want to understand the relationship between aerosols and dynamics, or aerosol and circulation. Obviously for practical reasons, because we want in future to do weather forecasting, for example, how to predict dust storms in advance for supporting robotic or human exploration. Then obviously, we are interested in the science itself. I will give you later the scientific question I'm particularly interested in. So the key factor to achieve continuous and simultaneous observations is the orbit of the spacecraft. By the way, by continuous observations or continuous monitoring, what we think of is like a very high rate, long-term monitoring. And by simultaneously, obviously, we mean like observing at the same time over a large area, right? if we have an aerostationary orbit, which is basically a Mars-synchronous orbit, which can even be like circular and equatorial, then we can observe a large area up to 80 degrees from the nadir point. Probably for the scientific purposes, it would be useful up to 60 degrees. And then we can provide a very high sampling rate, can get down to the fraction of the hour. And we can monitor throughout the daily and seasonal cycles. And that obviously is optimal for monitoring the very rapidly evolving meteorological phenomena like dust storms or ice clouds. But not only that, we can also, for example, use it, if we were geologists, we can use it to derive surface properties, take into account the variability of the aerosols, which is something which hasn't been done yet. Why? Because I can illustrate an example. On the left, you see a regional dust storms as if you were a polar orbiter. On the right hand side, you see the same storm as you were an aerostationary orbiter. They are the same data. These are real data. They are data of dust opacity taken from the thermal emission spectrometer on board the Mars Global Surveyor. The difference is that on the right hand side, I process them in such a way that you can achieve a kind of aerostationary-like view. So you clearly see that if you are a polar orbiter, you have gaps between the different orbits, and it's very hard to distinguish the dynamics of the storm. You see the opacity increasing, but it's hard to distinguish the evolution, precisely the dynamics of how the storm evolves. Whereas on the right-hand side, you are fixed, and you see the same spot for a long time. You can take measurements frequency you want, compatibly with what you can achieve, and clearly you see the onset and the evolution of the storm. That's the advantage we would like to stress with this mission. So what are the mission objectives? Personally, I think that the first question is compelling. We want to understand the dynamics of the dust storms, water ice clouds, and how these two phenomena are also leading to the onset of these very large global planetary scale dust events. But also, if we monitor the aerosols and the variability of the aerosols on the same area, we can derive the impact on surface temperature and derive surface properties like thermal inertia and albedo, take into account the variability of the aerosols. So what we plan is to put this Mars aerosol tracker in an aerostationary orbit. We want to monitor at obviously high sampling rate, the same fixed portion of the planet, at visible infrared wavelengths, and we want to monitor the evolution, as I said, the dynamics of dust storms, water ice clouds in particular, throughout the diurnal cycle. We will have access to day and night observations, obviously, if we use the right instruments. But also we can derive the surface properties, take into account the aerosol contribution and variability. How do we achieve that? We have a baseline spacecraft which has been designed by ExoTerra. Right now is in a particular baseline architecture, I will tell you in a second. It is a 45 kilograms SmallSat. It's not a CubeSat, it's slightly larger than a CubeSat. It's slightly larger than a 27U CubeSat. We plan to use an iris transponder with a capped antenna to achieve the best possible, so far at least, communication rate. We plan to connect it to an ESPA ring and use xenon gas as a propellant. The propulsion will be electric propulsion. ExoTerra has developed a halo, what they call it a halo. It's a micro thruster. Some numbers are given there, and they also develop their own solar array, which are deployable. So far, we studied three possible scenarios. The first one Case one is this simple one. You know, somebody bring us to Mars, does the Mars capture for us, and then we are released and we get into the aerostationary orbit. So this obviously is it's the spacecraft, which weighs less, 35 kilograms. The baseline scenario we are working on right now is the case 2. So we still need a ride share to Mars, but then we are released before the Mars capture. We do Mars capture ourselves, and we get into aerostationary orbit ourselves autonomously. This is the 45 kilogram spacecraft I was talking before. And then we also looked into a third case where instead of going to Mars with another spacecraft and mothership, we are just launching to GTO, geotransfer orbit, geostationary transfer orbit, and we do autonomous navigation to Mars, and again, we get into aerostationary orbit. Obviously, the delta V requirements are very different. The capabilities will change. We estimated some numbers. For the 3 cases, you see that the fuel allocation changes from 4 kilo to 11 kilo to 25 kilos of fuel. The delta V also changes from 1,600 meters per second to more than 7,000 meters per second. But again, the range are very large, and right now we haven't done an optimal determination of the optimal trajectory. So it's costly to go to Mars on our own. We know that. As the payload, so we are interested in looking at visible images, but also getting quantitative information about the amount of dust or water ice which is in the atmosphere. So we want a visible camera for sure, but we also want a thermal infrared camera because we want to retrieve dust and water ice opacities. So Malin Space Science System would provide us with the off-the-shelf visible camera that has from already some other mission. It's a 5 megapixel camera. The field of view is such that we'll cover the entire disk of Mars. It has a 4 kilometer resolution at nadir. As far as the 2 infrared cameras, these are the cameras that are still in development phase. It's a 0.3 megapixel camera, obviously the resolution is lower. It's a micropolometer based camera. It has the same field of view as the visible one, but the resolution is smaller, 16 kilometers nominally. We probably have to sum pixel in order to achieve a good signal to noise ratio, so the real resolution might actually be 65 kilometers at nadir. For the thermal infrared camera, we also have a filter wheel that will allow us to select different spectral ranges, because we want to simultaneously retrieve temperature at several levels in the atmosphere, and being sensitive to water ice and dust. Obviously, we have a buffer on board because we want to accumulate images as much as we can, and the products will be visible images, of course, during the night, but also maps of opacity, 3D maps of opacity, dust and water ice. Temperature will be retrieved because we need it for retrieving the aerosols anyway. And also we plan to have maps of thermal inertia and albedo corrected with the aerosol contribution. Because one of the main bottleneck is actually the downlink rate. As you see, the worst case is 20, not the worst case, the worst average case is probably 20 kilobits per second. We have an idea of planning 3 kind of observational modes. Continuous mode at lower resolution, and then for specific phenomena like monitoring water ice clouds or dust storms, will increase the resolution, but obviously we cannot keep it for long, otherwise we won't be able to download all these images. So I get to the final points, which are the challenges we identified in doing this concept from major to minor. Propulsion. Yes, propulsion is a major challenge. We initially thought about going for solid iodine. The technology is not ready yet, so we moved to xenon gas, but obviously we increased mass and volume. The thruster reliability is still to be checked. Communication is the second one. I think we talked about this before already. So we are planning to use JPL Capder, high gain antenna, which we plan to adapt to X-band. But still, the data downlink is not as much as we would like. Heat dissipation is a problem for everybody. We are a bit larger than a CubeSat, so we probably reduce this problem because we have more empty space in between components. Radiation is a big problem, particularly if we look into GTO case, because then we go through Malin and bands several times, spiraling out of Earth orbit. Data pre-processing, it would be nice to have an advanced detection of events so that we know in advance which images are interesting to download. And then obviously, launch opportunities is clearly a challenge. How many launches opportunities are there to go to Mars on the right share? How many? Station keeping is a challenge. We identified mitigation options. And I think with this last slide, I just put this a summary of our concept in terms of what we want to monitor, what we want to produce, and our baseline mission concept overview. And if you have a question, it's probably time to ask me. I will just add one little thing for questions if I can. Before we talked about communication platform, previous talked about sending a multiple network of CubeSats. I really think that if we had the opportunity to have a bus which has two things, propulsion and communication, and it brings several CubeSats on board, in this case to Mars, that would be a really great achievement, which would open a lot of pathways. Because in my case, I could reduce everything I presented down to maybe 12 CubeSat instead of going to an ESPA-class mission. And obviously, the cost would be reduced, and that probably more bandwidth to transmit information down to Earth. So I encourage anybody who's willing to work on this bus concept to Mars to go forward with this. Thank you very much.
Mentioned micro-hall process. I know one company in Italy was developing it, but wait for micro-hall. Okay, the micro-hall process. Do you have a certain technology already in mind, or a company who's developing stuff like that?
Which technology, sorry?
The micro-hall process.
Microfrost. This specific one is developed by ExoTerra. So I don't know about the others. Maybe this one is the one we chose. Maybe the others are developing other processes, yeah, for sure.
For the trajectory analysis to Mars, what software did you use?
This is something that ExoTerra did. I think they used the JPL software. But I can tell you the name later. I can check on this. But top of my head, I can't remember exactly.
Okay, software was very interesting. I got really inspired by the talk, and still have a really minor question. So, what's the sampling rate you are aiming for when observing the Martian atmosphere? So, yeah, for example, at a baud rate of 20 kilobits per second.
So, ideally for waterized clouds, we really want to go down to the half an hour frequency rate. For dust storms, we can even do if we really want to monitor dust storms during the evolution phase, we can do 1 or 2 hours. That's not a problem. But because of the communication rate, then we have to organize campaigns. So we cannot observe continuously at this rate. We need to have a few sols of waterized clouds campaign. The good thing is that we know when waterized clouds are forming, and we know that more or less the season when dust storms are occurring. so we can plan campaigns accordingly.
My question is a bit provocative, but please don't mind, because I heard the word in America. So did you change the paradigm? Here I see 3 payloads. You put it in a miniaturized way on a bus. Well, the paradigm is the same like previously. You try to make a mission the old way. So what is specific to CubeSat here?
Well, the cost. If you look at the cost.
But the cost is not only driven by the size.
Sure. No, it's driven by many things.
So
management, for example.
if you have 3 payloads on 3 CubeSats on board another craft, okay, that's a new paradigm. You see, so I'm wondering, could we do that with a swarm of CubeSat?
You mean like three on 3 CubeSats?
Yes.
Well, the point is we need the 3 payloads here because we want to simultaneously observe the same spot. So we wouldn't be able to separate these payloads on 3 different spacecraft because then we have so many problems of simultaneity. So here, the key point is that we see the same spot with 3 different payloads. And actually, the 2 infrared cameras are just because we had to split the thermal range and we couldn't use 1 camera for the whole spectral range. Otherwise, the initial payload was actually 1 visible and 1 thermal infrared, but then we had to split for practical reasons.
So you said that you could scale everything down to the CubeSat size, right? But the restrictions were propulsion and the antenna.
The main ones.
Right? So I remember another presenter proposed using a deployable antenna. Maybe that way you could save some space.
Yeah, we use this Captain antenna, which is a deployable antenna already, and it's going to be adapted to the X band. It might actually be adapted to transmit in the K band, so we still can gain some kilobits per second. Ideally, you will never have a big antenna as a big mission. So if you really want to downlink a lot of data, then you have to think about some strategy to reduce the amount of data at the source, before transmitting.
Really with some pre-processing as well.
Absolutely.
Okay, one final question, Daniel. Very nice pictures of Mars. I was wondering which part of Mars would you like to monitor?
Right. So there are 2 stable longitudes for aerostationary orbit, which I probably forgot to say that it's at 17,000 kilometers altitude. So one is about 18 degrees west, and then the other one is the opposite side of the planet. So obviously we'll aim for one of the stable longitudes first. By chance, it's also a very interesting spot on Mars because it's right at a place where dust storms are moving from the northern hemisphere, crossing the equator and evolving to the southern hemisphere. So we'll definitely look for that spot.